Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about just the basics of sine, cosine, and tangent functions and the beginnings of discussion about the unit circle. So just to go back and review the basic trig functions, we see that sine is the value of relative to the angle in question, the opposite over the hypotenuse, which in this case is y over r. And cosine is the adjacent, or x over the hypotenuse r. And then tangent is the opposite of the angle in question, y over x. So SOHCAHTOA, sine is equal to opposite over hypotenuse, cosine equal to adjacent over hypotenuse, tangent is equal to opposite over adjacent. Right, when we take a look at that in relation to specific values, again, we have y over r for sine, x over r for cosine, and then y over x for the tangent value. So opposite, it's always in relation to the angle that you're measuring or the angle that you're referring to. So sine would be the opposite from this angle measure, opposite side y over the hypotenuse, which is r. Adjacent side would be the side of x over r, and then tangent opposite y over adjacent x. So when we think about the unit circle establishes a radius of 1, which means that the hypotenuse, or what we had previously called r in the prior diagram, is going to end up being 1. So evaluating sine just becomes y over 1 or y, cosine x over 1 or x, and then tangent remains as y over x. So when we're finding the sine, cosine, or tangent of a specific value or point, what we want to do, our angle measure that's based on a certain point, what we want to do is we want to set up a right triangle. In this case, I've identified a point on the circle at 3, 4, and then I've drawn an angle from the origin with the terminal ray as the radius and the initial ray as the x-axis. What we want to do is we want to find the sine and cosine of that angle measure z. So, of course, you need the value for the hypotenuse in order to figure out both sine and cosine. And you can easily use your special family of Pythagorean triples to figure out that 3, 4, 5 is one of the Pythagorean triples, or you can use the Pythagorean theorem to find out that 3 squared plus 4 squared is equal to the hypotenuse squared, which is 5. All right, so we mark up the diagram. I know that 4, or you can just look at the diagram to see that the point 3, 4 means that the vertical change is 4 and the horizontal change is 3. So the sine of z ends up being 4/5. Cosine of z ends up being 3 over 5. All right, so now we're going to take another point on the circle. And then this is not a unit circle. We're just establishing a point. We want to find out the measure of z. And as you can see, z again starts from the initial ray, which is the positive x-axis, rotates in a counterclockwise fashion, which is the positive measure of the angle. All right, so again, we're going to establish what our lengths are for the side lengths, -7 and 9. And then we're going to use the Pythagorean theorem to figure out that 9 squared 81 plus 49 is equal to 130. So my hypotenuse length is equal to the square root of 130. And then we're going to place the value of y, 9 over the square root of 130, and cosine over -7 over the square root of 130 as well. But in order to fully simplify and express both values, we need to make sure that we rationalize the denominator. And so we're going to multiply both the numerator and denominator by the denominator over itself, or 1. I call this hair brushing. And what I mean by that is you always have the same number of hairs. When you brush it, it just looks a little bit different. And that's what we're doing when we rationalize. We're keeping the value of sine in its current state, but just expressing it in a rationalized form, which means that there's no radical in the denominator. So we're going to multiply 9 over root 130 by 1 root 130 over root 130. So again, we're multiplying it by 1. So I can rewrite sine as 9 times root 130 over 130, and cosine as -7 root 130 over 130. So now I've fully rationalized the denominator. And I say that the math gods instruct us not to leave radicals in the denominator. I'm sure there's a good reason for it. However, we won't go into it in this discussion. Just to say, at a high level, the math gods have established that writing rationalized functions or values need to express them without radicals in the denominator. All right, so now we're going to take another example, 1, -2. We're going to go through the same process. We identify the hypotenuse at root 5, the value of y at -2, and the value of x at 1. And so we see that sine is -2 over root 5. Rationalizing the denominator, we end up with -2 root 5 over 5, and cosine ends up being root 5 over 5. Another example, -10/8. Finding out that through the Pythagorean theorem, that the hypotenuse is the square root of 164. Simplifying that, take out a perfect square of 4. So now I have 2 root 41. My sine value is 8 over 2 root 41, simplified to 4 root 41 over 41. Cosine is going to be -10 over 2 root 41, or -5 root 41 over 41. Okay, so now we're going to talk about special angles, and the special angles are 30, 60, 90, and 45, 45, 90 angles. And we're going to evaluate what sine and cosine are based on what we know about 30, 60, and 90 degree angles, or 30, 60, 90 triangles. So in this case, we're going to start with a measure of our angle at 30 degrees. And in a 30, 60, 90 triangle, the side opposite 30 is always going to be valued at x. The side opposite 60 is x root 3. And then the length of the hypotenuse is always going to be 2 times the length of the side opposite the 30 degree angle. So we can use this information to figure out what the values of sine and cosine are going to be for any 30 degree angle or any 60 degree angle that is used as a reference angle. And we'll talk about reference angles next chapter. All right, so we see that x over 2x, sine of 30, is going to end up being 1/2. And cosine of 30 is going to end up being root 3 over, I didn't finish this out, root 3 over 2. So it's x root 3 over 2x multiplied by root 3, and you end up with root 3 over root 3, and you end up simplifying to root 3 over 2. All right, so this is the same function highlighted again, but just identifying the point on the unit circle as root 3, 2, comma 1/2. All right, so let's take a look at what happens when we have a 60 degree angle. Now the values are going to end up being reversed because the side opposite 30 now is the value for x. Hypotenuse remains at 2x, although this is considered to be basically a unit circle. And the side opposite 60 degrees is going to be x root 3. So let's go ahead and evaluate those again. Now sine of 60 ends up being root 3 over 2, and cosine of 60 degrees ends up being 1/2. Right, the last special family is the 45, 45, 90 triangle. And we always know that the relationship of the 45, 45, 90 triangle is going to be x for the value of x, or this leg, and x for the value of the other leg. Now we know that they're going to be the same length because these two angles are going to be both 45 degrees. And then the hypotenuse is going to be x root 2. So let's evaluate sine and cosine with this bit of information, and let's see if we can come up with a value for 45, 45, 90 triangle. All right, so we end up with both sine and cosine being 1 over root 2, which after rationalizing ends up with a value of root 2 over 2 for the 45, 45, 90 triangle for both sine and cosine. Now another question would be, what is the tangent now of 45 degree angle? And you can see that tangent would be root 2 over 2 divided by root 2 over 2, which is going to be equal to 1. So tangent of a 45 degree angle is equal to 1. All right, so sine of 0, 90, 180, and 360 degrees. You can see sine of 0 degrees, the y value is at 0, so sine of 0 is 0. And then rotating to 90 degrees, sine now is at 1 because it is or comprises all of the length of the radius of that unit circle. And then at 180, it's going to be 0 again. At 270, it's going to be -1. And then at 360 degrees, it's going to be equal to 0. And we should change that to 0 degrees, or to 0. All right, so sines and quadrants, just to review, sine of the first quadrant, and again, quadrants go in counterclockwise order in a positive angle rotation. So first quadrant is going to be positive cosine, positive x, positive y. Second quadrant is going to be a negative x and a positive y. Third quadrant, negative x and negative y. Fourth quadrant, positive x and negative y. So this is what it looks like. And then we're going to skip through to a couple more practice problems. We want to find the sine and cosine of z here again. So we want to find the value of the hypotenuse using the Pythagorean theorem. It's going to end up being root 10. Sine ends up being 1 over root 10, or root 10 over 10. Cosine ends up being -3 over root 10, or -3 root 10 over 10. Then a little bit more complicated problem for you. If z is a third quadrant angle, so 1, 2, 3, and z is equal to -5 over 13, so sine of z, so the y value is going to be -5, and the hypotenuse is going to be 13. Find, the cosine of z. So I'll give you a moment to try to figure that out on your own. All right, so I'm going to draw my angle, -5 for y, 13 for the hypotenuse. I can figure out that the value for x is going to be 12. Again, using the Pythagorean theorem, I know that the x value squared plus y value squared is equal to the hypotenuse squared. X squared plus 25 is 169. X squared is equal to 144. X ends up being equal to -12 in this case. So cosine ends up being -12 over 13. That's it for this edition of Ought in Math. Come back and join us when we start talking more about graphing trigonometric functions in 7.4 in the next edition of Ought in Math.